now jump into section 3, the bed load concept of sediment transport. So in our packet, we will discuss 3 main equations that are used to calculate the bed load transport in a channel. The bed load transport is basically the particles that do not come into suspension, that they travel along the channel bottom, just rolling or simply silting forward. And this quantity can be calculated 3 different ways, as I said. So first we have Einstein, of course, along with Brown in 1942. They did basically a probability analysis, summation, conservation of mass, and summation of forces equals 0, and they came up with this equation here. This is the main equation. They did not base this on any experimental data. So we have 40 times this K value, which is defined here, times the effective Schiltz parameter to the power of 3, times this term here, which is just a diameter d50 of our system and our specific weight. They came with this crazy way to define K. It results that it has a maximum value of 2/3 as the diameter goes to infinity, or it goes to 0 as the diameter goes to 0. So basically, the smaller the diameter, the smaller the bed load transport. In 1948, Mayer-Peter did some experimental studies and came up with this equation. He said that the bed load transport could be calculated as A times the effective Schiltz parameter minus the critical. Remember, this number is very small, relatively around 0.1, around there. To the power of 1.5 times this same term, which includes the diameter and the specific weight, gravity. Why not? What's important is this relationship. Kalinske and Frinchling came in 1952, and they did more experiments and tried to fit the curve to fit most of the points. They did even a more fancy relationship, which includes 2 times d50. This, as you may recall, is just the friction velocity exponent to the negative 0.27, and all these terms, even including the effective shear stress here. In the packet, you will see that the 3 formulas give very similar answers. In sediment transport, a similar answer can vary by 1 order of magnitude. That's what we're dealing with here. Very difficult situation to predict. So another important point to remember is this effective shear parameter that appears both in Mayer-Peter and Einstein. This effective Schiller's parameter, as you may recall, should be the friction velocity squared divided by s minus 1 dgd. And the friction velocity squared, what is that? Well, that is just the effective shear stress we calculated from before divided by rho. So generally, this term is very big relative to the critical shear parameter. So we use it in Einstein and Mayer-Peter. Kalinske here has a different approach. He uses the friction velocity, the total shear stress, and it works pretty well in general.